Very good morning to all. Myself, Dr. Indranil Dey, Assistant Professor, Department of Electrical Engineering, Holdia Institute of Technology. Today, I am delivering a lecture on design of feedback controller, mostly the PID controller. So, I'll start my presentation. Design of feedback controller. The first point is the design need specification. The common use of the design need specification to describe what the system should do and how it can be done. Let's say we have a process. For a particular process, we want to control some of its variable. So how that variable dynamics change, it actually can be decided by the controller specification. So when we are designing a controller, that actually uh, supposed to deal on the dynamics of the process output which supposed to be controlled. So these specifications are unique to each individual applications, and these specification includes relative stability, steady state accuracy or the error, and the transient response characteristics. In some applications, there can be additional specification on the sensitivity to the parameter variations, that is nothing but the robustness, and importantly, the disturbance rejections. Before we start designing of any control configuration, let's say uh, the the various types of control configuration available in control engineering. The first one is the feedback control. The most commonly used control strategy, it is the feedback control strategy. It is a setup where the output of the process is constantly checked, constantly checked, constantly checked against the desired reference value. The closed loop that actively maintains the desired output by continuously feeding back the information about the current state of the system. We'll describe it in the next slides how a feedback controller works. So next is a cascade control. It is a series or cascaded control of multiple feedback loops where they are connected in hierarchical manner such that it can most precisely manage the process. Next, the feed forward control. See, we have seen that the last slide that some specification can deal with disturbance rejection and the robustness of the parameter variation, robustness to the parameter variation. See, this particular control structure, control configuration in the feedback control, feed forward control, it can deal with major disturbances. See, if we talk about disturbances, a disturbance can be two types. One can be major disturbance, that is the known disturbance, and another thing can be unknown disturbance that directly impact on the process. So we cannot deal with the unmeasured disturbance, but by implementing feed forward controller, we can work and we can address directly to the process for the known disturbance to maintain the desired output without waiting for the feedback from the process. So we usually have feedback from the process, but for removing that known disturbances, we will implement a configuration, control configuration that is feed forward control. Feed forward control. Next is feedback feed forward. See, this particular type, feedback feed forward, is like a combination of two control loops where one can deal with reaching the desired set point and another one can deal with the disturbance rejection. So the combination of feedback and feed forward uh, make the system will be make the system more prominent, more precise to increase the overall performance and robustness of the control system. But by combining both, the system can achieve faster response while also retaining the stability and dealing with disruption very effectively. Now, coming for the fundamental principle of design. Once the control configuration has been selected, the designer must select a controller type. So that means we have several configuration for the control applications. After selecting the control configuration, we should go for a particular controller type. We have several options for that also, but we'll select it a designer, a controller designer first select the controller type, and after selecting the type, the elements of those controllers should be excuse me for a certain these elements of the controller should be uh, appropriately selected. So we have some rules for that. We need to do that properly, and after getting that appropriate value for those elements, we can say that our design specification is completed, so our goal is achieved. See, in terms of control practice, in industry's point of view, the engineers usually pick the easiest controller that works with all the requirements. Though I told that there can be some complex control configuration and controller also, which may be very costly. In same time, they are not that much reliable also. So that is why we should select a easy controller that will be very easy to design, reliable, and user friendly. And a complex controller is always very hard to build. Next, what is controller? So this is the main questions here. What is a controller? See, here I have given you two visualization, where the first visualization actually talks about the basic block diagram of control system. Here in this C, we have three red color blocks. Those are the three major element of control system. The first one is the plant or the process, for which you need to design a controller. And to design a controller in feedback structure, we have some measuring devices in the feedback element path. So let's see, this particular plant can have several outputs, but among that you should select one or multiple parameter to control. So then those parameters will be our control variable. So now we have the feedback path here. So in this feedback path, we supposed to use some instruments, some sensors, which usually measure the uh, process variable, which are acting as a control variable. So those variable will measure the data of the planned output and given back to the comparator. This comparator is nothing but an error detector. It will find out the difference between the planned output with the desired level of input. So by combining these two, we have generated a error signal. So what is the error? The error is nothing but the difference between the process output and the desired input. So that will be the input to the controller. So the controller will decide according to the error what type of control signal should be generated, and that directly affect to the plant, and such that it will regulate the output to reach this desired level. So we can say here a controller is a very crucial component that regulates the behavior of the dynamic system of the process. So let's say we have a one sort of example where a liquid level control system is supposed to be explained here. See, this is a tank. This particular tank can have several variables. As I told, for a particular process we can have several numbers of variables. Here maybe the concentration of the liquid, temperature of the liquid, height of the liquid tank, all are the process variable. Apart from that, we will select one particular variable which we want to control. So liquid level is our control variable. So the height of the liquid in the tank is our objective to control. So next we have a feedback element where we are measuring the output. So the output is nothing but here the height. So this height is measured by this measurement system which actually for this particular case will measure the height of the liquid in the tank, and that will give you in a process variable the actual data of the process variable given to the controller. See, in real practice, the controller itself have a comparator option which can measure the difference between your desired value or reference value with the actual value. So that error will be the input to my controller, and the controller will decide what control signal should be generated to reach the tank height to the desired level. So in that case, it will give the signal to the pump. The pump, which is basically our actuator, which will give more flow to the tank or less flow to the tank according to the need of the desired height. Let's say an instant where my height of the tank is 10 centimeter and my desired level is 5 centimeter. So the first instant, the measuring device, maybe a ultrasonic sensor or something, a capacitive sensor which will measure this 7 centimeter height. 7 centimeter is my set point, 10 centimeter is the actual height now. So it will measure and given back to the controller. So itself, the controller will get a error of 10 minus 7 of 3 centimeter if the 7 centimeter is the desired value. So you can see the plant itself have some error, positive error of 3 centimeter, where our reference value is 7 and actual height at that instant is 10. So that error of 3 will be the input to the controller, and the controller will generate a control action by its algorithm such that the pump will less operated to give less flow to the tank, such that the outlet from the tank will be more than the inlet, such that the height will reduce. It is a continuous process. It will operate it, and each and every instant the height of the tank is measured and given back to the controller. Then one instant come where the height of the tank will reach the 7 centimeter desired value. When it is reached the 7 centimeter desired value, the controller will try to fix the actuator, the pump, to maintain on that level such that the height should maintain in that 7 centimeter for a certain time. So this is a operation of a liquid level control system where a controller acts as a brain of this particular process to reach the process in the desired level. So in terms of controller, we can say controllers are very vital for ensuring the desired performance and precision in a variety of engineering and automation application. Next, so which controller is mostly used in industry? The answer will be the PID controller. It is fairly universally used control structure in industrial control. This controller is constructed from a specific structure controller family. So the structure of the PID controller is always fixed. So that is why it is called specific structure controller. Now the PID controller among all controllers have shown it is the reliable and incredibly useful for controlling a wide range of critical applications. The PID controller stands for P for proportional, I for integral, and D for derivative action. Next is why PID. As I told that we have easy, complex, so many options to choose a control configuration, control structure. Why I should select PID? Because of its simplicity and the user friendliness. See, as I see in the last PPT, that the structure of the PID is always fixed. So it is very easy to design and very easy to tune and deal with. So that is why it is very, very user friendly also. That is the reason this particular controller has numerous number of applications, which include semiconductor, aerospace, pharmaceutical, food, petrochemical, chemical, everywhere. Next important thing about a PID controller, its robustness. As you can see previously during the design specification, we have seen that a controller can deal with a disturbance which can affect to the process and the planned parameter modification. If it can deal with these problems, then we can say our controller is very, very robust. A PID controller is always unaffected by the disturbance and planned parameter modification. So that is the reason all the industry people usually prefer PID controller as a real-time controller action. But over 90% loop use PID. Some exception is there. One is on-off control. For loops with low control requirement, we use usually control like on-off controller. For old age thermostat, ACs, heating elements use on-off control where precision is not that much essential. But another option is the with the high precision control action. There we used advanced complex control applications for a nonlinear complex system. Apart from these two, we usually prefer PID control. So this is particular a structure of PID controller. From the block diagram, we can see that controller block is replaced by this PID block, where the process output is measured by the feedback and the difference between the set point and the actual process variable, which is the error, will be the input to this PID action. From the name suggests, P stands for proportional. What proportional? The proportional with the error. See, ET is the error signal, it is proportional to the error, and this Kp is the proportionality constant. Now from the integrator part, it is basically integration of the error signal. So that is the integration constant Ki, and it is the derivative of the error. So that is why it is the derivative constant. So combining all these three, we can have a PID control action which directly affect in terms of control signal to the process. So this is basically a PID block diagram where PID stands for proportional, integral and derivative action. So it's have a see if we talk about PID controller, a PID controller is nothing but a mathematical algorithm. A mathematical algorithm to minimize the error. So that mathematical algorithm will be derived in the next session. In the next session, we'll talk about mathematical application of PID controller. Thank you.